Initially, a bug sits on every square of a 5x5 chessboard. When a bell rings, each bug moves to a neighboring square, one with a common edge. So, for example, the bug here could move to here or it could move to here. However, and they can't move off the grid. But this bug has 4 choices of where to move to. And the question is, what is the minimum number of vacant squares? So, for example, the minimum number would be 0 if we could make that possible. Because if it were 0, that would mean that every single bug would move to another square and every single square would be occupied. Now, is that possible? Let's try. What if we say to move all these bugs in the first column to the second column and all the bugs in the second column to the first column, like that. Okay, so that gets rid of this, so there's no vacant squares there. Now, what if we do the same thing here? Okay, so then still no vacant squares, but what about here? Let's try there, okay? There, okay? But there's 1 square left. So we know, and this square must move, and then this spot will be vacant. So we know that our answer is either 1 or 0, because we can make the minimum value, we can make the number of vacant squares 1. But how do we know that's not 0? We notice that if we pair them up, since 25 is odd, we will always have 1 square left. So let's try a different strategy to try to get 0 vacant squares. So this bug, let's move it to here. This bug to here. This bug to here. This bug to here. So notice that here we're not pairing things up, but we're moving everything in the same direction, mostly. Try to keep going up. So that bug's moving here, that bug's moving here. So far, our plan is working. So far, there's no vacant squares except for this one. So we can keep going, so on. And then we'll get no vacant squares except for this one. So we just found another way to do 1. Okay. So we suspect that there's no way to get 0. Let's see if we can prove that. First, let's color the checkerboard. These squares, let's just color them green. So we know that there's going to be 13 green squares, and there's going to be a bug on every square to start. So, okay. So we know that there's bugs each of these places. And so we know that all the greens, these bugs, let's just color all the bugs that sit on the green squares. Those are purple bugs. And the bugs that are on the white squares, those are red bugs. So we notice something very interesting. All of the red bugs must move to a green position. And similarly, all of the purple bugs must move to a white position. So, let's take a closer look. So there's 12 reds bugs and 13 purple. Okay, so let's just see what happens after the exchange. After the exchange, each of the purple bugs is going to become red, and each of the red bugs is going to become purple. So after, there's going to be 12 purples, and there's going to be 13 reds. So that means that there's going to be 12 after the bell rings. That means that there's going to be 12 bugs on green spots. Exactly 12. But there's 13 green spots. So one of the green spots has to be left empty because there's only 12 bugs are going to be on green spots. So there must be a green spot that's empty. Because 12 things can't fit up 13 boxes. So our final answer is 1 because we proved that it's possible to get 1 vacant square. And we proved that it's impossible to get less than 1. That's it for